So we're dealing with momentum. We're going to be dealing primarily with linear momentum. So we are talking about an object. An object has mass and it's moving. Momentum, we give the symbol of lowercase p. Momentum is going to be equal to, and we just simplify it down to those two basic things, our m times v. If you want to think about this, a football player generally have a defensive side of things, and you also have the attacking side of things in terms of some football games. They are generally on the larger side of this. The reason for this, we want large people in football, is because they have a large mass. So that means that as a person running down in a football game, a large person running with a fairly high velocity, they have a lot more momentum. Therefore, it's going to be a lot harder to stop. We're thinking about a quantity that is explaining this. Example, I would have a larger amount of momentum. It would be harder to stop me than it would be to stop someone of a lighter mass. This is the basic idea of momentum. Different objects are going to have a different amount of momentum. A tennis ball would have a certain amount of momentum, and the little cup would have a different amount of momentum. What happened between the two of them? We had a muffin pan, it fell down, and then it hit the bench, and it stopped, right? Where we had a tennis ball, it fell down, it then hit the bench, and then bounced back up. When the patty pan drops and falls to the ground, it would go and it would become stationary, so its momentum would go to zero. What about the tennis ball? Is it traveling in the same direction? Does that mean that my momentum is going to be the same? Numerically, it could be, but directionally, it's going to be different. So we've got to be aware that our momentum is a vector. The ball fell down, it hit the bench, it then bounced up in the opposite direction. So if we have a momentum of the object that is traveling down at, say, 10 kilograms per meter per second, that is its momentum, it then goes up in the opposite with the same value. How would it change its momentum? It experienced a collision with the table. So if the table was not there, when I dropped the ball, it would have fallen down and it would have kept on going due to gravity. But because the table was there, it experienced a force applying it in the opposite direction. So a force can apply a change in momentum. What force am I talking about in this situation? Well, that was the normal force. But if we look at my equation for momentum, my SI units for this, my mass has an SI units of kilograms, and my velocity has an SI units of meters per second. So that means my momentum is going to be kilograms meters per second. But if the forces cause a change in momentum, what are my SI units for force? Forces, we do measure them in newtons, but newtons is not the SI unit. SI units for newtons is kilograms meters per second squared. So the difference between momentum and force is time. Because we've got kilograms meters per second, so there's only a -1 there, where in our newtons, it's kilograms meters per second squared. So if we want to see the change in momentum due to a force acting upon it, that force needs to act for some period of time. And this we call impulse. Impulse is going to be our change in momentum. So if we were to look at the change in momentum, we would be able to see the amount of force that's being applied for this. Can you change your momentum without a force? We can change our momentum by, in a sense, looking at our two variables that we've got in there. We have mass and velocity. There are certain situations where we can actually have a constant velocity and a change in the mass. It's not as easy, but we could also have a change in momentum with a constant mass and a change in velocity. So both of these are going to be possible, where our change in velocity is going to be our v minus u, final minus initial velocities.